Hello everyone, and welcome to the M2L31 Level 1 training course. Today, we will introduce the low-power timer, one of the peripherals inside the low-power domain of the M2L31 series. So, what exactly is a timer? As the name suggests, a timer is essentially a timekeeping module inside the MCU. It provides precise timing functions that you can use in many different ways. One common use is measuring elapsed time. You can think of it like a stopwatch. It keeps track of how much time has passed since the moment the timer was started. Another common use is generating periodic events. You can think of this as working like a metronome. The timer can generate interrupts or act as a trigger source at regular intervals. And the timer can also be used for countdown operations. This is similar to an hourglass. You set a target time, start the timer, and once the countdown completes, it will generate a notification or signal. In the low-power domain of the M2L31 series, there is a dedicated peripheral called the low-power timer. Its functionality is similar to a general timer, but it also includes an additional feature called auto operation mode, which makes it especially suitable for low-power applications. In the M2L31 series, there are two low-power timer modules, and each one is built with a 24-bit counter and an 8-bit prescaler. Each timer can also independently select its own clock source, giving you more flexibility when designing low-power applications. The timer offers 4 counting modes. Once the counter starts from 0, it behaves differently when it reaches the compare value. First, one-shot mode. The timer generates an interrupt just once and then stops. Next, periodic mode. After an interrupt, the counter resets to 0 and continues counting automatically. Then, toggle out mode. Similar to periodic mode, but every time the counter reaches the compare value, it also toggles the output pin. Finally, continuous mode. The timer keeps generating interrupts without resetting the counter. It counts continuously until it overflows, then wraps around and keeps counting. The low-power timer also supports event counting, allowing you to count events on a specific input pin. It has a capture function, which measures the timing of signal changes on a designated pin, for example, detecting how long a GPIO signal stays high or low. Additionally, the low-power timer can work together with the ACMP to perform internal capture and event counting, offering even more flexible timing applications. Let's illustrate how the timer works with a block diagram. The clock first passes through the prescaler, which divides the frequency before feeding it into the counter. The counter then starts counting. At this point, you can read the counter value or reset the counter as needed. When the counter reaches the comparator value, it can generate an interrupt. Other events, such as a signal change detected on a pin, can also trigger interrupts. These interrupts can be used for waking up the system or for interrupt handling. Additionally, the timer output can serve as an internal trigger signal, coordinating actions with other peripherals for more complex operations. In timer capture mode, the timer detects signal changes on a specified pin. When a transition is detected, it generates an interrupt and records the current counter value into the capture register. By reading the capture register, you can obtain the capture result and calculate the high and low durations of the signal. One important note: if you are reading the capture register directly through the CPU without using PWM, you must clear the capture flag to 0 first. Otherwise, the capture register will not be updated. The low-power timer provides 2 types of interrupts: timeout and capture. These interrupts can be used to internally trigger other low-power peripherals or to wake up the MCU from idle or power-down modes, enabling efficient low-power operation. The auto operation mode can be used under normal power-down levels 0 through 4. If you want to use auto operation mode to trigger other low-power peripherals, you first need to configure 2 registers: trigger enable and trigger source select. Once these are set, you can choose to use either capture or timeout events to trigger other low-power peripherals, enabling automated operations without CPU intervention. Unlike triggering other low-power peripherals, if you want to trigger the low-power PDMA, you need to configure two specific registers: Trigger Low Power PDMA and Trigger Source Select. Once configured, you can choose to use either capture or timeout events to trigger the low power PDMA, enabling automated data transfer in low power modes. Here are some commonly used APIs for the low power timer, which we've already covered in terms of their functionality. Low Power Timer Open is used to initialize the timer and set its counting mode and frequency. Low Power Timer Start controls the timer to begin counting. Low Power Timer Set Trigger Source and Low Power Timer Set Trigger Target are used to configure the auto operation mode. These APIs make it easy to set up and control the low power timer for various low power applications. Next, we'll move on to the PWM section under the low power timer, which we will refer to as Low Power Timer PWM for short. Each low power timer PWM has two selectable output pins. It is built with a 16-bit counter and an 8-bit prescaler. The PWM uses a double buffer mechanism, meaning both the compare and period registers have buffer registers to ensure smooth updates. The low power timer PWM only supports upcounting. It has two operation modes, similar to the regular timer. When the counter reaches the period value, it performs different actions. Additionally, the compare value is used to adjust the PWM duty cycle. One-shot mode. The counter stops counting once it reaches the period value. Auto reload mode. When the counter reaches the period value, it resets to 0 and continues counting automatically. The compare value is continuously compared with the counter value, and when they are equal, a compared point event occurs. Users can configure actions to take place when this event happens, including generating a PWM output pulse, waking up the system, or triggering other low-power peripherals. As shown in the diagram on the left, setting the compare and period values controls the PWM output duty cycle. The duty cycle is calculated as compare value divided by the period value plus 1. If the compare value is set to 0, the PWM output is 100% low. If the compare value is greater than the period value, the output is 100% high. For other compare values, the PWM output depends on the current counter value. It outputs low when the counter is greater than or equal to compare, and high when it is less than compare. The CMPBUF and PBUF registers are part of the double buffer mechanism mentioned earlier. When you change the compare or period values, the updates are loaded into the buffer after one PWM period completes. The first set of compare and period values is loaded into the buffer registers when the counter starts. There are several settings that control the overall low-power timer PWM output. PINV determines whether the PWM output is inverted. POEN decides whether the PWM output is enabled on the pin. POSEL selects whether the output appears on the low-power TMR pin or the LPTMR EXT pin. These settings give you flexibility in controlling how the PWM signal is output. The low-power timer PWM has two main types of interrupts. The first type is direct, not using the event accumulator. These are the interrupts we mentioned earlier, which occur when the counter reaches the compare value or the period value. The second type uses the event accumulator, allowing the compare and period interrupts to accumulate over multiple occurrences before actually generating an interrupt. Both types of interrupts can be used to trigger the LPADC or the LPPDMA, providing flexible control for low-power operations. This slide shows the block diagram for the direct interrupt mode, which does not use the event accumulator. By configuring the IFAEN register, you can select the interrupt source. When IFAEN is set to 0, the event accumulator is bypassed, and you can use PIEN or CMPUIEN to choose whether the interrupt comes from the period or the compare event. This slide shows the block diagram for the accumulator-based mode. The IFASEL and IFACNT registers are used to configure the accumulator parameters. IFASEL determines which PWM event, such as compare or period, will increment the accumulator counter. When the accumulator counter reaches the value set in IFACNT, an interrupt is triggered. The accumulator-based interrupt can trigger both the low-power timer interrupt and the low-power PDMA. Use the IFAEN and IFAIEN registers to select whether to trigger the low-power timer interrupt. Use the APDMAEN register to select whether to trigger the low-power PDMA. This allows flexible routing of interrupts for different low-power operations. In normal power down mode, another way to trigger other low-power peripherals is by using auto operation mode. Set TRGEN to enable the trigger function. Set TRGSEL to select the trigger source. You can choose the period point, the upcount compare point, or use both as trigger sources. This allows the low-power timer to automatically coordinate actions with other peripherals without CPU intervention. This slide is similar to the previous one, but when triggering the low-power PDMA, in addition to setting TRGEN and TRGSEL, you also need to set PWM TRGLPPDMA as 1. The rest of the configuration is the same as before. This ensures that the low-power timer PWM can properly trigger the PDMA in low-power modes. That concludes our training session on the low-power timer and low-power timer PWM. We also have video demonstrations using example programs for both, which you can find in the video list. Thank you for watching, and if you'd like to learn more, please feel free to contact us.